Hello, computer science principal students. I'm Monique Rice, and the topic of this video is logic gates. So let's just consider a switch. This switch turns things on and off. So our switch has two states, on and off. Remember how computer signals are represented by ones and zeros? Let's assume that on is represented by the number 1 and that off is represented by the number 0. There are three basic Boolean operators, and, or, and not. We will now explore the logic gates that represent these operators. We'll start with the NOT gate, and we'll demonstrate our result with the light bulb. So connecting our switch, which is our input, to the NOT gate, our output will be the state of the light bulb. So switch is off, light bulb is on. Switch is on, light bulb is off. So the NOT gate gives us the opposite of what we would expect, because normally if we turn the switch on, the light bulb would come on. But in this case, the switch is on and the light bulb is off. So for the NOT gate, or NOT Boolean operator, let's let T stand for true, which means that the light bulb is on. Let's let F stand for false, which means that the switch is off, the light bulb's off. And let's create a truth table for the NOT operator. Let's look at the NOT truth table. The input is the switch. The output is the light bulb. And when the switch or light bulb is on, that's represented by true, and the off state is represented by false. So when the switch was on, it resulted in the light bulb being off. And when the switch was off, it resulted in the light bulb being on. True led to false, false led to true. That's the NOT operator. The next circuit that we're going to look at is the AND gate. And notice that the AND gate looks a little bit like the letter D. But this time we have two inputs and one output. So we're going to add two switches for our input. And we're going to name these switches A and B. This is B. And we're going to use a light bulb to represent our output. Here's the light bulb. And remember, this is an AND gate. So A and B. So connecting this to the light bulb. Notice that A and B being off results in the light bulb being off. If I turn on the switch for A, now A is on, but B is off. Putting that through the AND gate, we still result in the light bulb being off. Turn off A, turn on B. Notice that the light bulb is off. Turn on both A and B. A and B are on, which makes our light bulb on. So the only way we could get that output to be on, true, 1, is if both inputs are on, true, ones. Let's look at the truth table. Here is our AND truth table. We had two switches for input, A and B, and we had one light bulb for output. The only way the output was true is if both A and B were true. Otherwise, our result was false. So false, false leads to false. False, true leads to false. True, false leads to false. True, true leads to true. True and true gives you a truth value of true. Okay, now let's talk about the OR gate. And notice that the OR gate looks a little different in that the sides are rounded and the bottom is also rounded. We're going to take a couple of switches for our input. One, oops, one, I cannot connect them. Switch one and switch two. And we're going to go ahead and add labels to our switches so we know which one's which. Here's my label. I'm going to call this switch A and the other switch B. And their output will be represented by this light bulb and whether it's on or off. Light bulb. And I connect that OR switch to the light bulb. So notice that if we have two switches that are both off, if we put it through the OR gate, it results in the light bulb being off. If we turn switch A on, then the light bulb turns on. If we learn switch A off and light bulb switch B on, sorry about that, then our result for the light bulb is on. And if both switches are on, then the light bulb is on. So the only way the light bulb doesn't turn on is if both switches are off. Any switches on results in the light bulb being on. The only way to get the light bulb off is if both switches are off. This is A or B. So here's the truth table for the OR operator. If A or B is true, if either A or B are true, then the output is true. This includes the case of both of them being true. We've talked about NOT, and OR, and we're going to talk about one more gate, and that is what we call the NAND gate. It's NAND, N-A-N-D, for not and. And when you look at the gate, there's that D for and then there's a little circle on the end. That's the not part. So let's pull out some switches for our inputs and see what happens here. And we'll label our switches once again, so I have a way to refer to each one. Oops, I don't know how to change it. Okay, so there's our two switches, and we are going to use a light bulb to represent our output once again. And so this is the output from the NAND operator. So, using the NAND gate, If both A and B are off, the two switches are off, notice that the light is on. If we turn on one of the switches, in this case A, the light bulb is on. Turn off A and turn on B. One of the switches is on, the light bulb is on. Let's turn on both light switches. Now that the switches are both off, my light bulb is off. So the only way to get an off in the NAND case is if both switches are on, which seems backwards, but it is, right? It's not and. And would be both switches on, light on. Not and, therefore, would be both switches on, bulb off. Here's a look at the NAND truth table. And notice that the only way to get false in this case is for both A and B to be true, or on, or ones. In every other case, our output X is true. So if you compare these values here in output X to the same values in the AND truth table, you'll notice that these are the opposites or the nots of the original AND table. That's it for this particular video on logic gates. We're going to move on to another video right now, but please start thinking about this. What happens if we have 3 inputs or a combination of some inputs? This has been Monique Rice from Advanced Kentucky. I'm signing off now.